Soto-Ontoso with us today. For those of you who have not met Alba before, she got her PhD from Granada and Frankfurt in 2018. She then moved to Brookhaven National Lab for her first postdoc. From 2018 to 2020, she moved back to Europe to Saclay for her second postdoc from 2020-22, and now she's at CERN. And Alba is an expert on various aspects of jets and heavy ion physics, and she has also a recent research interest on Parton showers. She has joined the so-called PanScales collaboration that she will tell us more about during this talk. And the topic of the talk for today, it's better Parton showers for LHC and beyond. So please, Alba, take it away. And thanks for agreeing to be with us.
Thanks a lot, Farid, for the very nice introduction and for everybody for attending this seminar. So the purpose of this talk is to convince you that the high precision that the LHC is achieving needs to be met by the theoretical community. And in order to do so, we need to reach sub% accuracy in our theoretical predictions in order to meet the statistical accuracy of the data. So a core component of any theoretical prediction for the LHC are Monte Carlo generators, that typically generate your exclusive events, and with that you can compute any observable, and one of the pieces of these Monte Carlo generators is the Parton shower itself, that is going to be the core of this talk. So before going into the theory, I just wanted to highlight how well the machine is performing. So the first plot that you see here on the first slide is just the integrated luminosity of what we have run during this first period of run 3. So it started at mid-July, so at the end of the summer. Then there was a stop because there was some problem with the magnets. It restarted, and now you see that by November, December, we are already achieving a factor 1.5 the expected, the targeted luminosity. So the machine is really functioning in a fantastic manner. A very high integrated luminosity means a lot of statistics and consequently a very precise data set, and for us theorists, a complicated job to achieve, to meet this statistical precision of the data. But this is not the end of the story, because if we look at how the LHC is going to perform in the coming years, the situation is, it's fantastic, but it's a bit scary even, because if we are, the luminosity that we have recorded is here right now in the year 2022, so this is where run 3 is going to take us until 2024, but this is just a tiny bit of the prospected luminosity that the machine will record during its it's supposed to be 6 runs. So by the end of 2037, we would have recorded 95% data more than what we have recorded today. So this is, despite the fact that the machine has been running for 10 years, well, 12 already, we are just at the beginning of the potential of the LHC capabilities. So yeah, 95% is still to be delivered. And again, what does it mean for us? What it means for us is that we need to provide theoretical support to this fantastic experimental effort. And how do we do that? Well, we could ask, so in order to understand which theoretical tools do the experiments need, an easy way to do it is just to take Atlas and CMS papers and check which theoretical papers do they cite most. So this is what you see here in this plot, that is the fractions of Atlas and CMS papers that cite a given tool. And we have color-coded this in blue and gray at the moment. Blue is quantum chromodynamics theory papers, and gray, experimental and statistical papers. So you see that already, I don't know, let's take PCI. PCI is cited in 50% of the papers of Atlas and CMS. And if we go to FastJet, for example, it's even like 80%. So clearly the tools, so QCD is the theory predominantly being used to understand PP collisions at the LHC. And in particular, if we dig a little bit further, and from the QCD papers, we select only the Monte Carlo generator ones, we see that, again, a vast majority of Atlas and CMS papers use these tools. So we can say that the Monte Carlo generators are really the QCD tools needed for the LHC. And these Monte Carlo generators describe in a completely exclusive way our PP collisions. So of course, the high energy process, as you will know, is a multi-scale process, and we start by the hard scattering at very high virtualities. This theoretically is described in the language of fixed order perturbation theory, meaning that you have a 2-to-2 process, and then you start computing corrections to this process in an expansion in the coupling constant. And we use the language of leading order, next to leading order, and so on. And there are a lot of tools in the market to calculate numerically this hard scattering process itself, and there has been a lot of development in the last 20 years in these fixed order generation codes. But now what happens from the super hard scale down to hadronization is that you have the fragmentation process. So from your super high virtuality partons, then you have to downgrade their virtuality down to hadronization, and they do this by emitting in a self-similar way gluons mainly. And this Parton shower, and this is encoded in the Parton shower inside the Monte Carlo generator. Nowadays, the language is not that of 1 to 2 splittings, but more of 2 to 3 splittings. So we talk about color dipoles in our Parton shower language, and the main players in these games of Parton showers are Pythia, Dyer, Sherpa, Vincia, and so on. And what I would like to address today in the talk is what's the status of these Parton showers. Essentially because they connect, they are responsible of describing the dynamics of the process from a very large scale to a very small scale. So we better have a good tool for the description of this process. And if we put the developments of Parton showers in the context of other QCD milestones, we reach this graph that I am showing here that I borrowed from Gavin, where he essentially checked what is the accuracy of given collider QCD relevant calculations as a function of the year in which they happened. So for example, the simplest thing that you can do in a Hadron Collider is just drill down. So you have your PP, you produce the set, and this cross-section was calculated at leading order already in the 70s. Nowadays, we are at the N3LO level, so extremely, so sub% accuracy in this fixed order calculation. If we take a look at another object in QCD, such as the Dirac splitting functions, again, we are reaching the N3LO. We are not there yet, but we are reaching the N3LO precision in the Dirac splitting function. What happens if we take a look at, instead of a fixed order type of calculation, a resummation type of calculation? So every time there is a pair of disparate scales in your problem, such as the hard scale and the hadronization scale, the presence of these two disparate scales generates logarithms that you need to resum in order to make the perturbative series convergent. And this resummation occurs in an expansion that is written in terms of leading logarithms next to leading logarithms and so on, and I will talk about them a lot in the rest of the talk, because we are going to make a connection between the Parton showers and these analytic resummation results. So again, the resummation, for example, in our Drejel process, the resummation of the PT of the set, for example, is known nowadays up to N3LL. So these are all just outstanding theoretical results. And if we look at the Parton shower status, it's a little bit more disappointing, because the field started more or less in the 80s, where they reach leading logarithmic accuracy. That it means that you are describing properly all soft and collinear emissions, or very small angle emissions. However, since then, not much has happened. Or to put it in a different way, a lot of things have happened, but they didn't converge yet into a higher precision shower. So from 1990 to 2020, there were parts of the next to leading log elements that one needs in a Parton shower, but somehow they were not ensembled together. So clearly, just by seeing these 4 categories, one sees that the Parton showers didn't see a development as quick as in the other theoretical calculations. So again, the purpose of this talk is to understand why didn't we reach next to leading log yet, and how can we reach it. And just to give a couple of more examples of the phenomenology where Parton showers matter, because you may wonder, well, maybe the data is not precise enough to be able to distinguish between a leading log or a next to leading log shower. Well, let me take just two examples. One of them is the extraction of the W mass, that is now a very hot topic due to this Tevatron measurement, but now I'm focusing here on the LHCb measurement. And to do this measurement, they need to calibrate the Monte Carlos with the PT of the set in other jam process. So on the left-hand side, where the plot says before fit, you see just the PT set distribution computed in different Monte Carlos and compared to an analytic prediction. And on the bottom plot, you see the ratio between data and the reference that they take here. And the first thing that comes to your eyes is that there's a wide spread in the calculation. So something a priori as simple as the PT set that is known analytically up to very high accuracy, up to N3LL. So this is not even the state of the art. The Parton showers that we have right now, or the Monte Carlos, at this stage is the Monte Carlo, you don't know if it's the Parton shower or not. The Monte Carlos that we have at the moment are not able to describe the analytic calculation. So what the LHCb does is just, okay, let's fit my Monte Carlo parameters to describe this PT set spectrum. And they manage very well, so they change the value of alpha S in the Monte Carlo and also the value of the intrinsic KT of the partons inside of my proton, and okay, it's true, they reduce a lot the uncertainty. However, this is not the observable that they use to extract the W mass. They use yet another observable. And of course, if you just fit your Monte Carlos to one particular observable, it doesn't guarantee that they will reproduce a second observable, because there are a lot of correlations between the partons that you are generating. And this is what no, I thought there was a question. So this is what drives the fact that, okay, for PT set, this Monte Carlo, more or less, agree now after the fit. Now I take another observable where I do my fit to extract the W mass, and these Monte Carlos spread again, and the error that they propagate into the measurement is comparable to the statistical uncertainty. So clearly, this spread of Monte Carlos is becoming a limiting factor, because the statistical uncertainty will be reduced very soon of this measurement. So the fact that this 17 is true, this is a very small error, right? Overall, it's like 17 maybe is a very small number, but still, this is driven by our Monte Carlo generators. For this audience, maybe a more particular example that I already showed in some talks is what happens for heavy ions. So, and in particular for jet observables in heavy ions. So a plot that I really like, and is from James in the audience, and when I saw it in Quart Matter, this is going to be my favorite plot for talks, is the one that I'm showing here, because it doesn't matter the observable, what it is a jet observable, and Alice measured the distribution of this observable in heavy ions. However, at the time, they didn't have the PP data. So instead of, well, in order to take the ratio from lead to PP, they took the ratio from lead to PCA. And this happened in 2018. And you see the ratio here, you see a strong modification of the observable. So you could interpret this as an experimental evidence of medium effects. However, years later, they were able to take a PP reference, just measuring the data, forget our Monte Carlo, and the discrepancy reduced a lot. So clearly, having a very precise vacuum benchmark is fundamental for any interpretation of lead data. And so far, all these examples that I have shown, you may wonder, well, but you are showing me discrepancies about between Monte Carlos. But a Monte Carlo is a multi-stage process. It's not just the Parton shower. You have the fixed order part, you have the hadronization. How do you know that the differences that you are seeing in these observables are really coming from the Parton shower? Well, the point is that the LHC right now is precise enough to distinguish between Parton showers. And the observable that I'm going to use to illustrate this is called the Lund plane. because essentially the Lund jet plane tries to reconstruct the Parton shower inside of a jet. So how this works is you draw in a plane the phase space for a given point. So inside your jet, you are going to have a splitting. This splitting is going to have a relative transverse momentum KT and a relative an opening angle 1 over theta. So if the splitting is soft and collinear, it will happen somewhere here around in the middle. If it's at wide angles, it will be close to this line. And if it's hard, it will be close to this line. So let's try to animate this thing. I have my first splitting that happens at formation time 1. How do I represent this into a Lund plane? Just by a dot. So I record the KT and theta, and I put a dot in my plane. I can have a second splitting and third splitting. Now, I can also have, these are all splittings coming from the hard prong. But I can also have secondary splittings. So splittings from a splitting, like this red line that I have here. And the way to represent this thing is just by spanning a new Lund plane out of the primary guy that was this red blue down here. Now we have a secondary Lund plane where my dot is there. And I can have a tertiary emission, and again, each emission spans its own Lund plane. And this can be iterated. So it's a very powerful tool to represent the phase space of emissions inside a jet. And on top of that, it can be measured experimentally, because you just have to take your jet, recluster with Cambridge agent to have an angular order sequence, and then start undoing your declusterings and record what is the KT and what is the opening angle of your splittings, and you put up a dot in your Lund plane. So this has been measured both for low PT jets and for high PT jets. So I'm going to focus first on the low PT jet measurement by Alice. And what is shown in this plot is just a slice of this Lund plane. So I fix the angle of my emissions, and I look at the KT distribution for a given angular beam. And here you have the data and comparison to several Monte Carlos. But out of the 4 Monte Carlos, from the ratio plot, you already see that there is quite wide spread in the predictions from some Monte Carlos with respect to the data. And what I find more interesting is this comparison between Sherpa, that is a Monte Carlo generator with a given Parton shower, and what they change is the hadronization model of the after the shower. And what you see in this plot is that the purple and green dots that do have different hadronization are actually pretty similar, meaning that what is driven the differences between Sherpa points and Pythia, or Sherpa points and Herwig, is not really the hadronization mechanism, but it's actually the Parton shower. So just from this plot itself, we can tell that the data is so precise and the observables are so differential that you can already discriminate between different Parton showers in your Monte Carlo. And also a very beautiful plot from Atlas is now, instead of taking a vertical slide, now you take a horizontal one. And they did the same exercise with Sherpa of saying, I take the same shower and I modify the hadronization, but also the reverse option to say, I take Herwig, I modify the shower, and I keep the hadronization the same. And what they see is that depending on the angle of your splittings, one of the 2 ingredients dominate. So when I am at very large angles, the Parton shower is the one driving the differences. It's hard to see here, but there are green crosses that are very well separated. And when I go to very small angles, it is in turn hadronization, because the crosses basically overlap, and now the filled triangles and the open triangles, they do not overlap anymore. So clearly, the LHC is already there in order to disentangle between different showers. So the rest of this talk is going to be about how to gauge the accuracy of a Parton shower, because it's not a trivial question, right? So with a Parton shower, you generate a set of an event record with all the form momentum of your particles, how you can construct arbitrary number of observables, how can you tell the accuracy of a Parton shower. And I'm going to introduce 2 types of tests to test this accuracy. One that is a fixed order test, meaning that you truncate the shower to a few number of emissions, and others that are all orders. So you let the shower run, and from there you construct observables. And now once I have introduced the criteria to gauge whether a shower is leading log or next to leading log, then I will show an explicit example of how to build a next to leading log Parton shower for E plus E minus, and in PP just for color singlet production, so for Drell-Yan. And there has been a lot of work in all major Monte Carlo generators, or in Pythia, in Sherpa, and in Herwig, that I will not cover for reasons of time, but here are the references in case you want to take a look. So the first, and before that, all the work that I'm going to present has been done in collaboration with all these people in the picture. That is, as Farid already said at the beginning, this is the PanScales collaboration led by Gavin Salam in Oxford. So the collaboration has different nodes. At the beginning, it was Oxford, UCL, Manchester, and Paris. But now, due to different reasons, a lot of us moved to CERN. So actually, CERN now is like as big of a hub as Oxford is it. So the power is really redistributed there. And the goal of the project is to bring this logarithmic understanding and accuracy to Parton showers. So the first test that we propose to gauge the accuracy of a Parton shower is relatively simple, because at the end of the day, okay, what is a Parton shower? It's an iteration of a 1 to 2 or 2 to 3 splittings, but ideally you would like to reproduce the exact matrix element. So if you truncate your shower just to one emission, you would like to reproduce the matrix element for that emission, at least in some limit. More concretely, if I just take one emission in my shower and I make it soft and collinear, I would like to reproduce this matrix element down here that you will recognize that has the soft and collinear divergence. So I'm going to keep on using this lumped representation, where essentially now I'm, again, the KT of the emission, the rapidity. So if the emission is closer to the quark, so I'm emitting from a quark-antiquark dipole, I emit a gluon. If the emission is closer to the quark, it will have positive rapidity. If the emission is closer to antiquark, it will have negative rapidity. And now if the emission is soft and collinear, since its matrix element is this thin, it will contribute in the logarithmic counting as an alpha S log squared. One log from the soft divergence, another log from the collinear divergence. So if you want to know if your shower is double logarithmic accurate, take your shower, truncate it to one emission, put it in the soft and collinear limit, and check whether it reproduces the matrix element. The question becomes a little bit more convoluted when you go to the next level of accuracy. Instead of double logarithmic accuracy, we want to check single logarithmic accuracy. In this case, sorry. In this case, we need 2 emissions at least to test this single logarithmic accuracy. And how are we going to do it? Okay, so if we want a single logarithmic accuracy, it means that we have to lose 1 log by definition. So we had our previous emission here that was soft and collinear, and in order to lose 1 log, we have to make it either a wide angle emission or a hard emission. Here, what we are doing is making it hard. So now our emission contributes to alpha S log instead of alpha S log squared. And now what's the idea? The idea is that if you have 2 emissions widely separated in rapidity, even if they have a commensurate value of KT, they cannot influence each other. In a more precise way, the matrix element for this 2 emission configuration, when the rapidities of the 2 emissions are very far away, so the distance in the loop plane is very big, reduces to the product of the 2 emission matrix element, 2 independent emission matrix element. So you recognize here the eta dkt over kt, the eta 2 dk2 over kt2. Again, if our shower is single logarithmic accurate, it has to reproduce this matrix element. When you have 2 emissions very separated in rapidity, they cannot influence each other.
Sorry,
why
Alba?
do I say this thing? Yeah, sorry.
I have a question. Did you define your log counting? What does double log and what does single logarithmic accurate mean?
Yeah,
Is it
so right
is
now,
it like the what does it mean, I guess?
right. So for
Is
me,
it in the
double,
exponent?
I didn't say the all orders counting. Right now, I'm just saying that double logarithmic is if it contributes as alpha S log squared. A single logarithmic is the emission contributes as alpha S log. But now I will do the all order counting. So this is just for
okay. So yeah, I was just confused because the matrix element you're down here is alpha S squared log cubed, which is not double log, but it's not quote unquote single log. It's just
no, it's NDL.
Yeah,
Right?
it's NDL. Exactly.
Yeah. So it's I agree. So for the logarithmic counting, let's go for the rigorous logarithmic counting. Let's go to the next.
Okay.
To the next. Okay, cool. So this is the fixed order part. Yeah, in which the general idea is, depending on where your emissions are in the Lund plane, you have to reproduce the exact matrix element when the emissions are well separated in the Lund plane, essentially. This will become clear along the talk. And now, what is the shower trying to achieve? Well, the shower at the end is trying to resum the same logarithms as what we resum in analytic resummation. So we still have this large scale Q, this low scale lambda QCD, and we want to resum all the logarithms that are generated from Q to KT cat or lambda QCD. So in principle, it should be possible to take your shower and compare it to an analytic resummation result. Now, how is this analytic resummation result typically look like for a very broad range of observables? The cumulative distribution for a given observable typically exponentiates, and the perturbative series, if you wish, can be written as an expansion in terms of the coupling and this logarithm L that would be again the ratio of the two disparate scales in your problem. Where the first term in your series is called leading log because it scales at 1 over alpha s. The second piece of your resummation is called next to leading log. And in this case, this thing goes as order 1. So if you want to do precision physics, this is the minimum that you can try to achieve is next to leading log, because otherwise, you are missing effects of order 1. And ideally, you would like to go to next to leading log, where now these terms are of order alpha s, so percent, 10% accuracy. And this is what the long-term goal is. But the rest of the talk is going to focus on next to leading log. Now, the question is, how do you compare? It's a bit tricky. How do you compare your shower with an analytic resummation result? Because, okay, you take your shower, your particles, you construct the observable that you want. In this case, it's called Y23. Doesn't matter what it is, really. And you take the ratio between the observable, the shower output and the observable. And you plot it as a function of this alpha s log variable. Now, what happens? Let's take Pythia, for example, and what we see is that the shower doesn't agree with the NLL expectation, right? So the ratio is not 1. However, one may wonder whether this is a pure next to leading log deviation or higher order effects are incorporated in the shower and not in the analytic result. So how can you discriminate between a next to leading log or a next to leading log? And the answer is actually relatively simple because we know how the perturbative series is structured, right? We know that the next to leading log compared to the next to leading log compared to the next to leading log is suppressed by an extra power of alpha s. So the trick is really just to take the limit of alpha s going to 0. So for a given value of my alpha s log, I start reducing the value of alpha s from the original value it was 0.02, now we go to 0.01, blah, 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 and then we extrapolate. Of course, you cannot run a shower that alpha is equal 0. So we run the shower to the minimum value that we can, 0.05 in this example, and then we make extrapolation. And in this case, if the discrepancy persists, it means that it's really a next to leading log deviation because we have suppressed, we have killed, not suppressed, we have killed the next to leading log contributions by taking this alpha s to 0 limit. So these are the two type of tests.
Question, Alba.
Yep.
Does it even agree at leading log? I mean, it could be a next to leading log deviation, but does Pythia even get this right at leading log?
Yeah, this observable, yes.
It does? Okay.
At leading color.
Okay.
Yeah, for this observable it does.
Okay.
I think we have probably I don't have the plot here, but there are plots for leading logs because it's a very good question. Like it can be already a leading log, but we typically test first leading log, then next to leading log.
Okay. Okay. Good.
Yeah. So these are the two tests that were introduced in this paper that we have here. So yeah, we can perform two types of tests to gauge whether a shower is next to leading log at the fixed order level. If our emissions are well separated in the loop plane, we have to reproduce the matrix element. At all orders, we should be able to compare the shower to analytical summation results for as many observables as possible, trying to cover all the kinematic regions in the loop plane. And if after taking this alpha s to 0 limit, they agree with the next to leading log result, we can certify, let's say, that the shower is next to leading log. And what is a recent development that I found very interesting is that these criteria were introduced in the context of the PanScales Parton shower, but I mean, you know, PanScales is a relatively new player into the game. Like the people from Sherpa, Pythia, and Herwig, they have been doing this work for a very long time. And what I found particularly interesting is that in the summer, the Sherpa team proposed a new shower, and in order to show that it was next to leading log, they actually followed our criteria, and they presented the shower called alaric, and they took essentially the shower, computed an observable, and take the alpha s to 0 limit, and they saw that their alaric curve seems to be next to leading log. Well, it's, according to them, is next to leading log, while dire shower that is in Pythia is not next to leading log, because you see that it deviates. So it seems that this language of logarithmic resummation is really entering into the community, and I think it's very good news for everybody, because it's it's gonna generate a new family of next to leading log showers in all Monte Carlo generators. Because of course, PanScales is a bit isolated, but these guys have it already implemented in Sherpa. I don't know if it's part of Sherpa directly, but for them, it should be easy to make it part of their framework where they have hadronization and so on. So I think it's very cool that everybody now is going in the same direction. And now that I have...
Alba, I have a question.
Yep.
So this test assumes that the alpha s is fixed, right? So there is no running of the coupling. Is there any subtlety if one wants to extend this test to include running of the coupling in your comparison?
There is running. There is running. What you fix
okay.
is the value at the hard scale.
Okay.
But there is running. Yeah. So to reach next to leading log, you need to loop running coupling.
Yep. Yes.
Yeah, sorry, this is a bit misleading. We should put alpha s parentheses q or something like this.
Got it.
Yeah. So now that the tests are clear, the natural question is, okay, how do you design something that actually meets, is able to meet these tests? And for that, I need to take a little step back and explain more or less how a dipole shower works. So I'm going to focus on dipole showers in Herwig. These Monte Carlo generators, they use an angular order shower, so 1 to 2 thing. I will not discuss that, and I'm going to use dipole showers for illustration. So I'm going to start from E plus E minus collision because it's simpler than PP. And the idea is E plus E minus to QQ bar, and at some evolution scale that I will denote V, a branching is going to occur. So I'm going to meet a gluon from my initial QQ bar leg. And how do we see this in a dipole language is, okay, I have a dipole composed by leg I and leg J. Pre-branching moment, I will denote it with a tilde. And after the branching, at least in the latency limit, you can see the gluon as part of 2 dipoles. So then I'm going from 1 dipole to 2 dipoles, and I am color connecting part of the gluon with my leg I and part of the gluon with my leg J. So now I have 2 color dipoles. And of course, since you emitted a new particle, you have to conserve energy and momentum. So either I or J or both have to absorb this momentum of the new particle that you just generated. And that's why there are some dashed lines here, just to say that they moved after the splitting. They don't follow the same trajectory. So what are the ingredients in this sketch that I just put here? The probability for this process to happen from a dipole I tilde J tilde to I J K can be written like in a very sketchy way, but I think it's enough for this. As well, a phase space factor, you have to parameterize your emission in terms of 3 variables, and we are going to choose the evolution variable of the shower. It is going to be typically a KT-like variable. an angle or a rapidity, eta bar, and an azimuthal angle, phi. And then this phase space multiplies the splitting function, that in this case is just really the Altarelli-Parisi splitting function. And since we have a dipole picture, essentially you have to decide whether K was emitted from I or from J. And to decide whether it was emitted from I or from J, what you do is to introduce an angular dependent function that essentially tells you if your emission was closer in angle to I. Let's describe it as if it was collinear to I. So just with like as if it was a 1-to-2 splitting, let's say. And if it was more collinear to J, then the same thing happens. So there are 3 degrees of freedom in this sketch that I put here. One is the choice of the evolution variable. I said that typically is KT, but it doesn't have to be KT, and we will see later why. A recoil scheme, meaning how do I redistribute the momenta after my emission, that it can be done at the level of the dipole itself. So at every branching step, you conserve energy and momentum at the level of the dipole, or you can go a little bit in an orthogonal direction and do a global recoil in which all particles in the event, every time there is an emission, they recoil. They take some transfer momentum recoil. So we are going to explore these 2 options, a local recoil scheme or a global recoil scheme. And then the definition of when do you assign the emission to the I side or to the J side of the dipole is driven by the definition of this eta bar variable. So how do you define well, this function and the eta bar variable itself? And the key point is that the choices that you make here in these 3 degrees of freedom actually affect the logarithmic accuracy of the shower. So we are going to start by Pythia, or Dyer, well, essentially the state-of-the-art dipole showers in E plus and minus collisions to say which choices did they make. So for the evolution variable is a KT, like a variable. For the recoil scheme, they do this energy momentum conservation at the dipole level. So you see the emission here, it generates a K-perp component, and the emitter, that is I, in this case, we denoted it by I, it absorbs the K-perp with a minus sign, and the spectator just takes some rescaling of its energy moment, of its momentum. And now, this definition of the dipole partitioning is done in such a way that the value of eta bar equals 0 corresponds to 0 rapidity in the dipole rest frame. And this is crucial, as we will see in a little bit, the fact that this partitioning is done in the dipole rest frame. So in order to check how this shower work, let's go to, although I showed you already that they are not nextly locked, but let's take a step back and show why, in fact. And we are going to do just 2 expansions. So order alpha is the square of the shower, so a type of fixed order test. And what is the next to log expectation? Well, as we said before, if I emitted a gluon already, height. This. So if I emitted a gluon here and I want to emit a second gluon, I expect that if my second gluon is very far away from my first gluon, it should be the quark or the anti-quark, the one that recoils. But it cannot be the gluon himself. Why? Because if it is the gluon, then we are going to break down this assumption that these 2 emissions are independent. Because if my second emission pollutes essentially the kinematics of my first emission, then I am not fulfilling anymore the fact that the matrix element has to be the product of the independent emission matrix element. A different way of seeing this is by color coherence. So essentially, typically color coherence that, okay, you have your gluon, put a cone around it, it can only be affected by emissions inside of the cone, and inside of the cone, it should be generated with a CA color factor. Outside of this cone, it should be a CF color factor. So it's a different way. And yet another different way is with the Lund plane. That is going to be useful, I hope. Again, same variables, KT and rapidity. And what we expect is if my gluon, my second gluon, is generated from the first one, so from the secondary Lund plane that the first gluon has generated, then it's okay if my gluon recoils, right? Because it's really within the cone of my first gluon. If it's next to the quark, it should be the quark taking the recoil. If it's next to the antiquark, it should be the antiquark taking the recoil. In other words, if we see it here in a more, well, not Feynman diagram, but a sketch, another sketch, I had my first gluon here that was hard and relatively at large angle. This guy, these kinematics, cannot be modified by a collinear gluon that is happening close to the quark. If it's happening close to the quark has to take the recoil. And what Pithi and Dyer do is actually not correct, because they give the recoil to the gluon in a huge region of phase space that they, well, huge, in a logarithmically enhanced region of the phase space. So this whole region that I colored in red is where they give the recoil to the gluon. In other words, if we go back to our sketch before, instead of giving it to the quark that you saw here that it tilted a little bit this trajectory, now they are giving it to the gluon itself, even if the two emissions are far away in rapidity, as this was first observed already in 92, not for PTI and Dyer, but that this problem existed was observed in 92. So if we do a little cartoon, imagine that I put a second emission here, where the antiquark should be the guy recoiling, and instead it's going to be my first gluon that is going to be bouncing around when it shouldn't. When it shouldn't, because this emission is far away in rapidity. So this automatically breaks this the two emission matrix element, because essentially my KT1 pre-branching and after branching is not going to be the same. So this is going to be breakdown. And the origin of this problem is the fact that they partition the dipole in the rest frame. So the consequence in the rest frame of the dipole. So the consequence of this is that you are giving the recoil, or in this cone picture, you are making the cone too big, because you are ascribing the radiation to be closer to the emission in regions of the phase space where you shouldn't. So this already concludes that the showers in Pithi and Dyer are not next to the log, and the question is how to solve it. One thing that you can do is to keep this local recoil scheme idea, is to say, I want to keep still redistributing momentum at the level of my dipole. So then if you want to fix the problems of Pithi and Dyer, you have to do two things. The first one is to realize that this eta bar equals 0 value, it cannot be 0 rapidity in the dipole frame, but it has to be in the event rest frame. So what this means is that you are drawing the bisector between your first gluon and the quark, and then you are assigning properly the recoil on this side between the quark and the gluon. However, the choice that you are making here doesn't fix the problem completely when your emission happens at larger angles. Well, completely no, it doesn't fix the problem when your emission happens at larger angles. So in order to solve this wrong assignment of recoil, you have to do a second modification, and is instead of having a KT order shower, why is it a KT order? You can see that the contour for the emissions are horizontal. So this means that it's a KT order shower. Instead of having a KT order shower, you have to modify the evolution variable, essentially introducing an angular exponent. So now your evolution variable is going to be a KT exponential some rapidity and a free parameter called beta, and beta can vary. In practice, only for values of beta between 0 and 1, we reach next to the log accuracy. So the evolution variable is now something like KT square root of theta, or something like this. So it's it's not KT, it's this thing. But what is the advantage of this thing? Well, now instead of having a flat contour as KT, now we are tilting the contours, because we are introducing this dependence of eta. And the fact that beta is positive automatically guarantees that if you were not doing the right thing here, when you had a first emission and a second emission at larger angles, what this choice of evolution variable does is just to swap them. So essentially, emissions with commensurate KT are radiated ordering angle. So who was 2 here with the new ordering scale is going to become 1, and 2 is the old one. And in this case, automatically you fix the problem because we knew that from the right-hand side of 1, everything was working okay. So these are 2 tricks. It's not like a most elegant solution that you can ever do, but this is how we solve it. Is a practice way of solving it. It's just by changing the partitioning of the dipole and the evolution variable of the shower. An alternative way of solving the problem is by performing a global recoil scheme. So again, instead of sending the KT to the emitter, as we were seeing before, like every time you emit, the emitter recoils back. Now, let's only rescale the emitter and spectator by some factors and give the transverse recoil, so you keep longitudinal momentum conservation at the level of the dipole, but transverse recoil is distributed over the whole event with a Lorentz transformation. And this Lorentz transformation, essentially, so with a boost, ensures that more energetic particles recoil more, because also it wouldn't make sense that a gluon that is extremely far away in rapidity from this emission is going to take a recoil. That's not a physical picture either. And then we keep the dipole partitioning in the same way as for panlocal, and the evolution variable again the same, but the fact that the recoil is global allows us to have a KT ordered shower. So now beta can have values of 0. And then probably you have seen this plot already, because this proof, so this is the validation. All that I have discussed before is a fixed order a picture. So just with 2 emissions, playing with the recoil of 2 emissions. And now here we really run the shower, compare 2 observables, take this alpha s to 0 limit, and check for a bunch of observables deviation of dipole, so of Pythia, our panlocal with beta equals 0, that also doesn't work, and the rest of the showers that do work at next to leading log. So they agree perfectly with 0 in this case, because it's a relative deviation. So this was the E plus E minus paper. On top of that, we have also subleading color contributions and spin correlations that I want to talk about. But recently, what we have been doing, so this was 2020, from 2020 onwards, what we have been doing is to extend this paradigm to PP collisions. And what's the complication with PP collisions is that you have way more dipoles. So you start with your initial partons, now your initial parton. So you have to take, essentially you have to take into account the backward evolution from your hard scale back to your proton. So your initial partons can radiate a guy, and now you have, after this emission, you have 2 types of dipoles, an initial final dipole and a final initial dipole, depending on whether you emit from this side or from the other side, and also a final dipole. So you have a proliferation of dipoles. On top of that, you have Parton distribution functions, but the rest stays more or less the same. So there's a same idea of splitting the soft singularity with the legs of the dipoles stays the same. And for the first papers, we work just with color singlet production. So what I call here X, that is my hard system, is going to be a Higgs or a set boson. Again, we did the exercise of comparing with what is standard on the literature. Now we call it dipole KT, it's more generic. It's not PCA, is not dire, it shares ingredients with them, but we call it dipole KT. And well, these 2 types of dipoles are not relevant at the moment, but there is some guidance from analytic resummation on how the initial final dipoles should work. Because essentially, if you want to generate the correct, so how does the set generate its transverse momentum? Well, because every time you have an emission from your initial legs, the set recoils and is acquiring transverse momentum due to your initial state evolution. So if you have, the idea is that every time you do an emission from an initial leg, the set has to recoil. However, if you want to describe the PT set at next to the log, and this was noted by Parisian Petroncio in 1979. However, there is still options in the Monte Carlos to work with a local recoil scheme for this IF dipole, meaning that the set is not going to recoil, it's only going to be the emitter or the spectator or whoever. So this is definitely wrong. Next to the log still is part of the Monte Carlo generator. And the other option is to do a global recoil that I will explain it later with PanScales. But again, the problems are going to arise because the dipole partitioning is still done in the dipole rest frame. So if we run all order tests for this type of dipole KT showers, what you are seeing here, instead of just 1 point, because before I was just showing the value for a given value, showing the big plot where I showed not next to leading log and not next to leading log, I was just showing 1 point of this distribution. Now I'm showing the whole distribution. And again, if you want to be next to leading log, you have to be at 1, and you see that it doesn't matter. So if you do this initial final dipole in a local way, the recoil, of course, you are wrong. We knew this from the beginning. By doing it in a global way, you fix the problem a little, substantially, not a little bit, substantially, but still, you are not next to leading log. Another observable that we took a look at is the azimuthal angle between the leading jets. And here the discrepancies, you see that they can rise up to 60% discrepancies from the next to leading log expectation. So the default shower are not next to leading log. And what we did was to fix, again, the problems of these showers, but there are a lot of subtleties in a PP context. Due to time, I will not go a lot into the details, but essentially the pan-local and pan-global showers for PP are not just a straightforward adaptation of the A plus and minus. There are a lot of ingredients that one has to take into account. So the philosophy is the same, but for example, in pan-local, every time you try to conserve momentum at the level of the dipole, you have to be careful because you have an incoming Parton that has to have 0 KT after the evolution, right? Because it's going to read from a Parton distribution function. So every time you emit and you generate a KT, you have to realign your event such that your incoming Partons are always aligned with the set axis. And in this realignment process that you do through a boost, this is how the set is going to get a recoil every time there is an emission. The dipole partition stays the same, evolution variable the same, as in E plus E minus. Now in pan-global, we do it completely different to the E plus E minus, because in E plus E minus, we were distributing the recoil over the whole event. Now we just boost the hard system. So every time there is an emission, all the transverse momentum goes to the hard system, in this case, the set, and the longitudinal momentum, the component is restored by rescaling the incoming guys. And the rest stays the same. So the dipole partitioning and the evolution variable stays the same. And now if we go to the all order tests, we have, I'm going to focus, we did it for many observables, but just focus on the PT set distribution, well, the color singlet PT spectrum. This is the same distribution as I just showed you before for dipole KT, that I told you, okay, for local we knew that it was going to fail, but for global is a little bit better. And now pan-global, so the pan showers essentially are on top of 1. So they demonstrate that they are next to leading log. And also for the Higgs, you can see some differences due to the color factors that are interesting to understand. We don't only do just distributions and to see numerically that one is next to leading log and the other is not next to leading log. There are also some observables for which you can tell qualitatively that they are not gonna get the correct next to leading log behavior. So what I am referring to is, instead of just taking the PT set spectrum for all values of PT set, now we are gonna take the PT to 0 limit. Because this PT to 0 limit is very well known in resummation, and the power law behavior of this small PT set to 0 limit is completely under control in PQCD. And what we see in this plot down here is that, well, the pan-local, pan-global, and dipole KT with this global recoil, they manage to get something flat. Dipole KT gets completely wrong, the power law. And however, we see so that the slope is the same for these 3 curves, but the normalization, we also know how to calculate. So the value at PT equals 0, essentially. And even if dipole KT gets the correct slope, it doesn't get the correct normalization. What I wanted to transmit with this plot is that you can go a step beyond and not only like numerically check whether a binary decision is next to the log or not, but really qualitatively you can see the discrepancies in this distribution. And finally, probably the most interesting part. Yeah.
What is the color singulate mean? In what sense here? Singulate mean?
So just that we are producing a set boson. That
Okay.
you don't have color in your final state of the PP collision.
You only look at the final state as just Z boson. Okay.
Exactly. As the Rayleigh, yeah, we don't have jets in the final state.
So this is sort of like semi-inclusive process. You only look at the Z boson spectrum, right?
Yeah.
Okay, thank you.
Yeah. So it's really the Rayleigh, essentially. And what probably is more interesting in general is, okay, you have a shower that is next to the log, cute, very elegant, theoretically nice thing, but how does it impact phenomenology? So we are not yet in a position to do phenomenological studies with our showers because there are missing ingredients that I will list in the next slides, but we wanted to see whether the theoretical uncertainty of a shower is reduced after including these next to the log terms. So typically, as in a resummation calculation, what you do is vary the scales, the renormalization scale, the factorization scale, you multiply them up and down by a factor of 2. And we took the ZPT spectrum, this is the whole distribution, as a function of PT set, now far away from the asymptotics. We are no longer in the asymptotic regime, we are in the physics world again. And what you see on the bottom plots are the ratio to the central value of this envelope that we see here. And again, the envelope is generated by a scale variation. The first cool thing to notice is that two next to leading log showers, so pan global and pan local with beta equal 0.5, have a very different error band. So it's small in both cases compared to, well, let me focus. The first message is, if you compare next to leading log showers with leading log showers, clearly the uncertainty is reduced. So for sure, having a next to leading log shower helps you to reduce the uncertainty of your theoretical calculation. Now, what is even more interesting is if you have two next to leading log showers and you see a discrepancy between them beyond the asymptotics, this is telling you about the size of the missing higher order terms that you don't, well, not missing, the terms that you do not control in your shower. So by comparing pan local and pan global, or pan global and erratic from the Sherpa team, we could get a sense of how big these higher order corrections are. And this is extremely valuable information to know, yeah, how important are these next to leading log. Yeah. So this is at this point, this is all we can say about the phenomenology. And why cannot we say more? Well, because we are missing quite some things. The first is we need to match our showers to the hard matrix element. So essentially, we first need to do a next to leading order or next to leading order and match to the shower. This is almost done. We need masses for the quarks. Right now, yeah, everything is massless, so we have to put masses into the maps and also on the coupling. We need to interface our shower to a Monte Carlo generator. The easiest one is Python, so we are already working on that. And when you put the shower, a new shower into a hadronization, and link it to a hadronization model, you have to retune it and so on. And of course, because LHC is way more complex than just Drell-Yan, so we are working towards Z plus jet and dijet in PP. And once we have these 4 bullets, I think we will go public. But this is just the first step because the real goal is to go beyond next to leading log. So it is already took a while, but I think, or we think, we are now in a position to go one order higher in accuracy. And for that, we need both like reference calculations or resummations at next to leading log to compare to our shower and also understand how these logarithms affect the recoil properties of the shower in the soft and in the collinear limit. But I would say that there are going to be exciting prospects for phenomenological studies with these more accurate Parton showers. And that's all I need to say. Thanks a lot for the attention.
Thank you very much, Alba, for this interesting and timely talk on the efforts of the PanScales collaboration, especially considering the wealth of experimental data that is going to come from the LHC in the upcoming years. Let me first clap in behalf of the audience. Thank you very much.
Thank you. I
And
cannot
now,
see you. No.
now we have some time for questions. So does anybody have questions for Alba? You can go ahead and unmute yourself and ask directly if you wish.
I have one question, if I could. Yeah, thanks for the nice talk. Really exciting work. I have a question kind of about your thoughts, eventually getting back to the question of jet quenching and heavy ion collisions. Because I'm wondering to what extent we can try to get some understanding or guidance from the theory side of like which observables might be better or worse under control for these effects. Because for jet quenching, I mean, if we just try to forget as much as we can about precision PP physics and some of those things that you talk about, and just think about understanding the jet quenching process, the theory really needs to just like accurately capture the difference between the PP and AA. Obviously, like the AA shower modifications, there's all sorts of things people will do. But my question then is, if you have thoughts on like whether it's useful or feasible to try to study and provide some theoretical guidance, like which observables might be better under control and like already say with like leading log showers, and which observables like really might require these higher order showers.
With PP, I mean, yes, I don't have well, maybe I can. You can see my screen, right?
Yes.
Yes. Yeah.
So I'm gonna 1 second. This is not very. I should have it in the backup, but I don't have it. So there are some observables for which Pythia actually gets the next to leading log because of there are some azimuthal cancellations where there are a lot of explanations why do they get it, and in principle this should be safe. If I go.
Alba, we are looking at your slides right now. Are you trying to show?
Sorry. Yeah, let me share my whole laptop.
Okay.
So there are some showers, some observables. Well, this is not very illuminative. Probably it's better the E plus and minus paper. But well, essentially there are some observables for which the Pythia showers work very well. So I don't remember on the top of my head what are these things right now. I know that there are like some sort of angularities, but I can tell you which ones Pythia should be close enough to next to leading log to be safe on that side. And,
right, but even
yeah, sorry.
Sorry, so I want to ask even like a slightly different question. Like this, you can ask the question of in what cases for PP is leading log good enough, but supposing that I just want to understand like the modification from PP to AA, I might be able for certain observables to like on an absolute scale not have a very accurate PP theoretical description, but I can still model like the difference as well between PP and AA. So I'm wondering like certain observables, I mean, like, I'm just wondering if this is something in parallel to developing better showers, whether you think it might be useful to try to better understand like what jet quenching observables really need that precise baseline and which you could kind of get away with a less accuracy.
Right. I will have to, because I mean, ideally, if you would have access to the Lund plane and you could take a slice of the soft and collinear part of the Lund plane, this should be okay. This, I think we understand how to go from PP to heavy ions, but for that, you really need to unfold the Lund plane. I mean, this would be the most differential thing that you can imagine, but this stripe of the Lund plane, you should be able to describe it for sure, from PP to heavy ion. Now, it's not being that differential, I would have to think, to be honest, a bit more carefully to give you a proper answer. I don't know right now. No, sorry.
I see, okay.
Thanks, James. I have a question about going to digit observables. So now you're going beyond this color singlet production. And I suppose the difficulty there is that you have more dipoles, right? So now you have color partons also in your final state. Is that, and I guess that's also important if you want to have baselines for PP when you want to study phenomena in heavy ions, because one typically looks at jets. So how much more difficult is to tackle this case of color octet?
Right. So if we start only from the set plus, just the two set plushes, so 3 color particles in the final state, the complication of that thing is, well, for pan-local, not much, but for pan-global, where we are assigning the recoil to the hard system, it was very easy to define the hard system where you only have a set. But now, if you have a set and a parton, your hard system is evolving after each evolution scale, because you can have radiation from your jet initial parton, and you have to decide how to update this hard system. What are you going to call the hard system? But at the level of color, and because also I didn't say, but we are doing things at full color. So set plus jet at the level of color is not an issue. We know how to extend the method that we have to set plus jet, but from the recoil point of view, we are now testing whether, depending on your prescription to update the set plus jet system, you can screw up the next to the log accuracy. Because, okay, so if the jet is the one radiating, it's clear. You can have, you automatically call it part of the hard system, but you could also have an initial state emission that is very hard. Why couldn't this be a part of the hard system as well, if the KT of this emission is commensurate more or less to the KT of the jet? So that's the complication in set plus jet. And now in dijets, on top of that, is the color. Like 4 particles, if you want to do full color, it becomes very complicated. So probably I don't know if we will be able to do it in the short term, or probably we will release something with leading color. It's not clear yet. At the moment, we are on the set plus jet side. But yeah, the four legs process with color is very tough.
And I can help but ask a question about the EIC. Could you somehow use some of these techniques? Are you thinking in that direction as well?
I mentioned it, but 2 of my colleagues, at least, have been working on that a lot. And there is going to be next to Lady Log Shower for the IS in the coming months, essentially. I am not involved wrong decision in my life. I am not involved into that project, but they are making a lot of progress already. And there, the cute thing is that you have to keep in touch the transverse momentum of the photon, essentially. So your T-channel change, you have to keep it untouched. Every time you do an emission, you cannot touch the photon at all. But there you have an initial final dipole. You start from there, and then you start radiating. And yeah, they are testing right now whether this is next to log or not. But there will be for sure.
This is also under PanScales, or is okay?
Yeah, there are a lot of parallel things right now. I'm working on the masses, Pythia, and the PP shower, but we are a lot of people, so there are crazy things going on.
And I have one more question. Maybe it's difficult to answer. So in one of your slides, you show the uncertainty, the theoretical uncertainty for the extraction of the. So I think it was one of your very first slides. So I'm not sure if the question. Yes. So and the uncertainty there was commensurate to the current statistical uncertainty. So can you give us a ballpark of how much would this theoretical uncertainty be reduced with the efforts that the PanScale collaboration is making?
Right. So we cannot do an apple-to-apple comparison because this plot would be equivalent to this thing that I showed here. But we are being very careful with the on how to transmit the message about the phenomenology, because we know that there are many things that we don't have yet. And for example, all these curves here in this plot, they have matching to the next to leading order, I think, most of them, at least the black dashed line, they have matching to the exact next to leading order matrix element. And this already plays a role, not in the low PTZ region, but in the high PTZ region. All these people have hadronization, we don't have hadronization. So I cannot give you the number right now. It could even be, I mean, it's true that you can put a lot of these things of the accuracy under the carpet of hadronization tuning. So I wouldn't be surprised if at some point you take PanScales, you put it with Pythia, and we get a worse description of the data. It could perfectly be, because if you don't tune anything, it could be the, but again, the selling point, I would say, is that the theoretical uncertainty is way more under control, because if you see all these curves are without theoretical uncertainty. So all the showers, nobody, people are speaking about theoretical uncertainty, but they are not really working on that. So these curves are just plain, you take your Pythia, run it, and what it gives, it gives. But there are scales that you don't control, and there are higher order terms that you don't control. So you should have a way of understanding what is the size of this effect. So yeah, I guess this number would be higher if instead of just taking the central value, they really vary the scales within the within the Monte Carlo. But to give you a number, I can't. Unfortunately, I cannot.
So what you're saying is that with PanScales we will have a more honest, systematic way to address the theoretical uncertainties that what is currently thrown under the carpet right now. Okay.
Yeah.
Thanks, Alba. Do we have any final questions for Alba?
I am happy to sleep.
Yeah, it seems like we don't have any more, but I encourage you to reach Alba in case you have any questions. And thank you very much, especially because we know it's very late in
Thanks,
Geneva
Alba.
right now.